So the plan for the next 2 weeks, we've kind of hit the end of some of the stuff we're going to hit about MySQL. And, in reality, we've still only scratched the surface. There is a lot to know when it comes to databases, as I'm sure you're kind of finding out. That's a process that you can learn. I've been learning more and more about bases for years. And SQL especially, because there's just so much to the syntax and so much that you can do with a database. But we've kind of got to take some time to talk about some additional topics. So that's what we're talking about this week. And so this week we're going to be focused more on security related topics, namely authentication and authorization. So those are the big two topics for these next 2 weeks. But we'll be hitting some additional things along the way that are sort of related topics. So our end goal is that we want to provide users a way to log into our website securely. I mean, that's the main kind of thrust and goal of this lecture, is to get from where we are right now to doing it actually securely. And to manage those user accounts and provide those login and register screens in a way that really follows best practices, best security practices, and such. So in general, when we're talking about authentication can be a lot of things. But this, what you see here, is the most common form of authentication. It's your usual login screen with the username and password field. That's your just basic, most common form of authentication that you see. This is one way to do it. You provide me the username and password. I look at that. I look into my database and I say, okay, yes, that username and password appears in the database. Oh, so you're user 23, right? Because that has that username and password. That's kind of the simplest version. And if I don't find that pair, then I just say, what you provided me is invalid, right? So it's always basically a true or false. Either your credentials are valid or your credentials are invalid. That's any way we do authentication, it's really always a binary result. Yes, you're good, or no, you're not. That happens with any form of authentication that we do. Authentication can come in a wide variety of forms. Common ones you'll see with login forms would be a username plus a password, or oftentimes you also see an email plus a password. Some fields, some websites, they actually support both. So you can either type in your username or you can type in your email into that first field. But I'd say most of them, largely, it's one or the other. So your email obviously ends with things like @Gmail, @Yahoo, @Hotmail, etc. But your username doesn't have if it's a username, you don't have a domain name at the end. Does that follow? So for instance, if I'm logging on inside Ranken, I log in as PR Smith. If I'm logging into my email, I log in prsmith@ranken.edu, right? So some places I use that email, sometimes I use that username. Okay. So those are usually closely related. In general, your email is obviously selected on an external website. Your username generally is one that you've selected on the website where you're logging in. So those don't necessarily have to be the same, but oftentimes you find that, like I use the username paulsmithkc and my email is paulsmithkc@gmail. But I don't always use that username. Sometimes I use other usernames, but the same email. Credit cards is also actually, anytime you're dealing with credit cards, that's also another form of authentication, as it turns out. So like if I provide you my credit card number and the PIN code, that is authentication. That's authentication that you use to prove that you can use that card, right? Some newer cards have chips, right? So you have the credit card number and you've got the PIN code, but that PIN code then goes through the chip and it does a little bit of encryption hashing to add another layer of security in there, because you can't kind of do it unless you have that chip. You can also purchase things like credit cards. Sometimes you need your credit card number, your expiration date, and your CCV code, right? If you're buying things online, that's usually what they ask for, right? Still, other places, sometimes you give them your credit card. They'll take the information off of there, and then you sign you put your signature. So all of those things, are different ways that your credit card might be used for authentication. Now, on the next slide, I'll kind of give you what a definition of authentication is, but you should start to see that maybe this idea of authentication is a little bit more broad than just username and password. Let's say we're talking about smartphones, especially lock screens, although this doesn't always appear on the lock screen, it may appear other places. Generally speaking, when you're logging on your smartphone, you don't have to provide a username or email address. You usually just have to provide some sort of secret, right? So whether that be a 4-digit PIN or some sort of pattern that you draw on your screen connecting the dots, it could be a fingerprint, it could be facial recognition, it could be other things. But generally, all of those are kind of options for you to unlock your phone or potentially use other apps like your banking app, for instance. You might log in with your fingerprint or things like that. So all of those things fall under the umbrella of authentication. So if you go to the dictionary and ask, well, what is authentication? How do you define this term? You might get a definition like this. Authentication is the process or action of proving or showing something to be true, genuine, or valid. So that's the broader English sort of definition. Authentication is proving that something's true. In computing specifically, we narrow that down a little bit, and we generally say that authentication is the process or action of verifying the identity of a user. So generally, when we're talking about authentication, we're talking about proving your identity, proving that you are who you claim to be, right? So my authentication mechanism, if I'm logging in, it's proving that I am Paul, that I'm Paul Smith. If Paul Winka is logging in, it's proving that you're Paul Winka and not letting you do things. Similarly, Troy, if you're logging in, it's proving that you're Troy, right? Because you don't want somebody to impersonate another person, right? So the whole point of authentication is to prove your identity and to prove that you're not impersonating somebody else. So another definition that may be a little bit more closer, I pulled this from a website called TechTarget, which is more IT focused. Authentication is the process of determining whether someone or something is in fact who or what it declares itself to be. So proving that you are who you claim to be is that big part in there. Authentication technology provides access control for systems by checking if a user's credentials match the credentials in a database of authorized users. So in general, we'll take whatever credentials you give and go check that against the database and make sure that they're all good. And then that will either give us a yes, it's all good, or no, at least one of them is wrong, so you're invalid. All of them have to be right.
How about those CAPTCHA forms?
Those CAPTCHA forms are they proving your identity?
No.
No, they're not.
They don't really prove. In some sense, in general, I would say they don't prove your identity. In reality, actually, sometimes they do. Sometimes those CAPTCHAs are actually, there's actually a little bit of authentication built into there with the more advanced ones. And that's maybe something to dive in later. But in general, no, CAPTCHAs are not, at least simple CAPTCHAs are not authentication. But at the same point, they're kind of, what are they there to prove? They're there to prove you are a human, right? And not some sort of automated process. So maybe they are a little bit of authentication, right? Because they are proving that you are a human, and human is part of your identity, right? So yes and no. It depends on how you define authentication and how broadly you define it. So sometimes those CAPTCHAs may be part of authentication, and sometimes they may not be. But they're not largely there to, Generally your CAPTCHA is not there to prove that I am Paul Smith, right? It's just to prove that I am human. Okay. Users, as far as talking about authentication again, users are usually identified with a username, and authentication is accomplished when the user provides credentials, maybe one credential, maybe more credentials, for example, a password that matches that username. So that's the general, most common way you see authentication, is you provide me a username and a password that matches it, and then I go check it. So let's talk about something called authentication factors. And you may have heard this term before, maybe in the terms of two-factor authentication, right? I'm sure you've run into that term at some point. Two-factor authentication means that you have two factors. But what's a factor, right? I'm sure you've heard the two-factor term, but maybe not heard what a factor is. So before I define factor, I might need to define one term quickly. Authentication credentials. Each piece of information that you provide in the authentication process is known as a credential. Every piece of information you provide is a credential. So, for instance, if I have a login form with a username password, how many credentials am I asking for?
2.
I'm asking for 2. I'm asking for a username and a password. Let's say we have a password reset form, and I ask you for 3 security questions. I ask you to answer 3 security questions. How many credentials is that?
3.
3, because I asked you 3 questions, right? So you can kind of think as a credential as a field in that form. But sometimes your credentials are provided in other ways, such as maybe hidden fields or cookies or other avenues. So the number of credentials you have doesn't necessarily always exactly the number of form fields. Or if let's say I'm registering an account, maybe not all of those necessarily count as quote unquote credentials in some sense, or I might not use all those credentials that I entered on my register form on my login form. In general, we can take all of those credentials and categorize them into a few different factors. So factors are a sort of category for your credentials. Okay. The most common of those 3 are going to be knowledge, possession, and inherence or inheritance. I've seen that third one called different things. But in general, the way that we usually talk about them is something, it can either be something you know, something you have, or something you are. Now, there's additional factors nowadays that you can use as well, such as location factors and behavior factors, and those are relatively new additions to the authentication game. But they're worthwhile things to consider if you're building a secure system. Most systems don't have location or behavior factors, but some more secure system may. So there are also things to consider. Okay. So something generally means, it's not, we're talking about knowledge, things that you know. So that can be things like a username or password, right, is something you know and something you can provide. Although your username often isn't private, it is still something you know. Cool?
Yep.
So it fills in there. Passwords, PIN codes, CCV numbers, patterns that you enter on your smartphone would all be, all those things would be considered knowledge. Because if someone else were to know that, they could act as you, right? It's just something you know, but somebody else could know that, right? And therefore they could pretend to be you, right? Similarly, security questions are things you know. If you're asking, what was the name of your first pet, right? That is something you know. right? But it's not necessarily perfectly secure, all of these, because somebody else could guess it or find it out through a different source.
Do you think that a lot of like the challenges that go around on Facebook, like the where you grew up type stuff, it says like, oh, what kind of dog did you have? Who was your favorite teacher? Do you think that's all just scams to try and get your information?
Some of it, yes. I wouldn't say all of it. I would say a lot of times that's passed around innocuously by people that are just like trying to have a little bit of fun and learn about people. But especially when I look at some of those questions, yeah, I would be concerned about that. You know, if you're asking me about my first pet or, you know, previous cars or, you know, even things like what's your birth date, then I get suspicious, right?
Yeah.
So a lot of times I would say that those are largely intended as innocuous sort of things. But you do have to be wary from them from a security standpoint, because if they're being used if that answer is being used as a security question, well, it's probably not something you want to share on social media, right?
No, not one bit.
If the name of your first pet or the name of your first boss or things like that, or the make or model of your first car are things that you're using as security questions for your bank or somewhere else, that's probably not something you want to mention on social media, because sometimes, you know, sometimes it's easier to exploit the password reset functionality than actually figure out somebody's password. That's oftentimes true. Which part of why when you do password reset functionality, we usually don't immediately give you your password, right? If you enter those 3 security questions, it usually doesn't pop up on your screen and say, okay, your password is this, right? Or okay, now you can go set a new password, right? Oftentimes it's like, okay, you answered the security questions, now check your email, right? Because I can come in and answer your security questions if I know those answers from whatever public record, and there's a lot of public record out there. But I mean, I shouldn't have access to your email, right?
Yeah.
If it's a text message or email, I shouldn't have access to that. Now, there have been cases where people have worked around that. There's been some big name Twitter accounts and YouTube accounts where because the attackers were able to go and transfer the phone number to one of their devices without having to prove that they are the right person. I know several years ago, Linus Tech Tips, if you know their YouTube channel, they had this problem. Somebody went to like a Canadian telephone company and they said, here, I want to take this cell phone, buy a cell phone and get the cell phone number transferred. Well, they transferred the number and then they reset the passwords on their Twitter account and social media accounts, and therefore now they could get in, right?
That's a big rip for Linus Tech Tips.
Yeah. Well, they fixed it. They admitted they did a YouTube video about it because it's actually a common problem, because most people do that, and that's considered, at least two-factor authentication, which is still is generally considered kind of the gold standard, right? That's being more secure, but the problem is that it relies oftentimes on your phone number, the assumption that your phone number is yours and nobody can take it from you, right? And
yeah, I guess in a sense, if they take your phone number, that's almost a case of identity theft.
Yeah, it is for sure, and that's where things become. That's kind of the chink in the armor in a lot of websites at the moment, is that relying on that phone number being secure is not necessarily the best thing. But either way, the point is we usually don't use those security questions by themselves, because a lot of times the security questions are easier to answer than figuring out what your password is. So we talked about knowledge factors. Possession are things that you have, things that you own. So that can be things like the magnetic strip on the back of your credit card, or it could be the magnetic strip on the back of your badge, right? For Ranken, if you want to get into the doors, right, you swipe your badge, which has a magnetic strip on it, right? So the assumption is that if you're not a student or faculty or staff at Ranken, you don't have that badge, right? So every time you swipe your badge, you're kind of authenticating yourself using that magnetic strip. And generally, everybody has a different number on that strip, which means that anytime you swipe it, basically security knows who's there and at what time did they enter the building. Smart cards also are things you own. So, whether it be a SIM card chip that you've, put into your smartphone, or it be a smart chip on your credit card. Both of those things are effectively things you have to own, because if you don't have it, you can't prove your identity. The other things that you can use for possession are things like security tokens. You can see one here on the right. These are actually these security tokens are actually one of the best ways to really secure your account at the moment, because they really do rely on that thing of like, well, you have to have this, and if you don't have it, you can't get in. So a lot of websites support these kind of tokens. Some of them are USB enabled, where you can plug them into your USB port, and it has to be plugged into your USB port to use it. Other ones are just kind of dumb like this, dumb digital displays, where they just give you a number and you type that number in. Those codes that kind of prove who you are, and they generally cycle based on time. So if you look at your security token, you'll get one number. You look at it again a few minutes later, you'll get a different number. So they're kind of a way of generating what we would say is one-time token, one-time codes you can only use once. Although those numbers might be repeated. Other things you might see in the possession factors are authenticator apps. So most game companies have these, or in some way, shape, or fashion. Blizzard, I know, has one. You can and they suggest locking your account with an authenticator app. So if you don't have that app installed on your phone, you can't log into your Blizzard account. Overwatch game, or you can lock WoW, so you need that token to get in. You need the authenticator to get in. Steam has a similar thing. They call it Steam Guard, and so you have to have that. If you have that set up, then you can't get into your Steam account without that authenticator application, which generates a code. So in general, the biggest thing you see here is one-time codes. Most of them generate. You'll see things like that, one-time codes with, let's say, hey, this is the first time we've seen your computer, right? So they might send you a code to either email or your phone number to say, okay, let's prove that you're actually who you are, and then enter that code. I'm sure you've seen that on a bunch of websites by now. So those security codes that are sent out, that generally falls into possession factors, because like the code in theory would be something but it's really, you can't get the code unless you own the device. So it's really about possession, not about knowledge. The third most common factor that we see is what we call inherence. And this is things that you are, something you are. And in general, this is when we're talking about something you are, we're talking about biometrics. So you're proving things by your biometric attributes. So that can be fingerprint scanners. That can be retina scans, which we've had since the 90s, and you'll see at some secure facilities. That can be newer things like facial recognition. Facial recognition's been around for a long time, but we've only recently started to use it for authentication. Maybe you've heard about this idea of Windows Hello. Windows Hello lets you log into a Windows machine just by looking at the screen, right?
Yeah, surfaces use it.
Surfaces use it, and really you can use it on any Windows 10 computer that has a camera.
It's very stingy though on laptops like mine. Like if I wear a hat,
Uh-huh.
sometimes it won't even pick up my face. Like I'll have the
Yeah.
same face, same glasses, same outfit. I wear a hat, and it's like, who are you?
Yeah, there's a happy there with facial recognition. There's this kind of medium of like how much difference do you allow, and how much difference do you not allow? Because let's say you allow, let's say okay, well I allow people with hats. Did I then introduce a problem where there's enough gap where person A can log in as person, person B can log in as person A?
I definitely see the upsides to keeping it like way stingier than letting just a little bit of flexibility in there.
Yeah. Is they've had some problems where it was not stingy enough, actually. Windows Hello has had some issues. Other things that you have to watch out for is, well, what if I hold up a photo of your face? Right? Does that count? Am I you? So a lot of things you have to watch for there. There's also things like, well, what happens if I walk past the computer, but I don't actually stop and sit down in front of it, right? Do I need to measure the distance between the screen and you and determine that you're actually there and meaning to use it? So there's a lot of ways that can be exploited. But it is one authentication mechanism that's being used, right? You're proving who you are by your face, right? So some smartphones, you're talking about services, use that. I think Apple has done a similar thing with facial recognition at some point as well. There's also voice recognition, which is kind of hit or miss. It's not perfect, but your like Google Home and your Alexa devices, you talk to them and they listen to your voice to try and determine your identity, right? So, for instance, we've got some Google Homes at home. If I talk to them and ask them about my calendar, I get one set of results. If my wife talks to it and asks for their calendar, she gets different answers because Google Home is kind of authenticating based on our voice. Cool? So all of those things can, be authentication mechanisms that you use for really any application that you write and build. Some of those mechanisms, especially the biometrics, is a little bit harder to implement on websites, right? It's a little bit harder to implement voice recognition and facial recognition, retina scans. Those are a lot harder to implement for websites because they require specialized hardware. But it's not saying that you can't do it. Other factors that you might consider, you can actually look at their location and use that potentially as part of your authentication scheme. So location, there's kind of two key ways to look at that. You could look at their GPS coordinates, right? Say you have a smartphone, you've got a GPS chip on there. You could look at their latitude and longitude and say, well, you're trying to log in this account from China. Well, that doesn't make sense. Or from Russia or wherever it may be. It's like, well, your user, you normally only ever log in from United States. This is probably not you, right? Or you might see things, you talk about streaming, maybe you can't watch a certain show on Netflix because or wherever you are, right? So your location can be a factor in there as well. Sometimes you don't have GPS coordinates, or sometimes you care more about the network architecture. You can also kind of use their IP address. There are techniques to take an IP address and get a rough location from that. Kind of, I think within a, say, 10-mile radius, you can usually get from their IP address. So that can be an indication of their location as well. Okay. So you can implement things like geofencing, where you say that you can only log into this website if you're in this geographic area. You might do that with their GPS coordinates, or you might use their IP address to do things like that. You can also do things with the network architecture. Say you've got a private network. Ranken has a private network. There's a website that we can only get to if you're on that network. It's called our intranet. So that sits kind of in the private network. There's a firewall that would normally prevent you from getting in there. But you can also then use VPNs to kind of get and be on the other side. Sometimes that location factor is implemented by the way the network is structured by some networking tools. So places you might see things like that. Let's say you have a server, you have your database server. You probably don't want everybody logging into it directly. So you might do things like say, hey, your database can only be connected to by this IP address, right, which is your web server. So only your web server can connect to your database. And that prevents other outside actors from connecting directly to it. So those are things to consider. We can also have things like behavior factors. Behavior factors is kind of a rare one that's used, but it actually provides a lot of security. Now, I say it's rare because most websites don't implement it directly, but actually, if you've ever used reCAPTCHA, reCAPTCHA is actually a behavior factor. It does things that are closer to authentication and less like a CAPTCHA. So if you've seen this box, I'm sure you've seen this a few places. You check the box and you say, "I'm not a robot," right? And oftentimes that's all you have to do, right? Just check the box. How does that work? How does me checking the box prove that I'm a human? Couldn't a robot check that box?
It's a special box.
Okay, why is it a special box?
Maybe just it's somehow hidden from the computer or something. I don't know. I just know it's special.
Okay, so the robots can see it. Everybody can see it. It's not hidden from automation.
Is it based off of click speed or something like that?
A little bit. It's based on how you behave. So in general, when we're talking about behavior factors, we're talking about like the time and speed of your mouse movements and your keystrokes and your mouse clicks.
Do they?
Yep.
Are they more on the side of like how fast does it take him to analyze this, move his mouse over, and click it versus typing it in versus a program that could automatically know what to do already?
Right. Yes. It has to do with how fast your mouse goes there, how it goes there. Does it go there in a straight line? Does it go there in sort of a squiggly curve? Because, humans don't move their mouse in perfect lines, right? And they don't move it at a constant rate either, right? And they also don't do things like teleport, right? So Google, which now owns reCAPTCHA, has implemented a lot of smarts behind that reCAPTCHA checkbox that does look at how you move your mouse and uses that to determine who you are. In fact, it doesn't just say if you behave this way, you're a robot. If you play this way, you're human. It actually keeps track of to the point of kind of giving you an identity. And it says, have I seen this person before? So if it hasn't seen you on this website before, it will generally ask you to go do the CAPTCHA challenge. And then the next time you come and visit that website, generally the next time you just check the box. Because the first time you did the CAPTCHA challenge, or the first 1 to 3 times, it paid attention to how you moved your mouse and saved that information. So the next time you go there, it looks and says, well, does your mouse movement the same as how you behaved the previous time, right? Is it normal for you? So Google is actually saving a certain amount of data anytime you fill out a reCAPTCHA form, because it's actually saving your mouse movements, at least some of the behaviors there. Linus Tech Tips, actually, they've got a channel that they do a lot of videos about this. So since it's already been asked about, I do want to show this video that kind of talks about how reCAPTCHA works. So a little bit about CAPTCHAs and what the reCAPTCHA system works like now. So behavior factors is kind of that fifth leg now in your factors that is relatively new, but there are definitely some good things that you can do with that. And if you've ever had a case where maybe you went to a store and your bank said, hey, this is unusual activity on your account, right? That's your bank kind of looking at behavior factors, right? So even banks are paying attention to this and the location as well for like, hey, you're making an overseas purchase. Is this really you, right? Because they care about you proving your identity and, only, only accepting those transactions that are actually you. So we've got 5 factors we talked about. We talked about knowledge, which is, something you know. We talked about possession, which is something you have. We talked about biometrics and inherence and things you are. We talked about a little bit about location, and we talked about behavior factors. So anytime you have an authentication scheme, that authentication system is going to use a collection of those factors and credentials. So if we look at the normal login form, the username and password, well, both of those two inputs, both of those credentials are knowledge factors, right?
Yeah.
So if that's all my authentication scheme is, this is, on the one hand, this is a simple system implement, and you can implement it when everybody's anonymous, with respecting people's privacy. But it's not a terribly secure system because it only relies on that one factor of knowledge, right? So let's say you have your username as in your usernames and passwords in plain text in your database, right? Well, then anybody who has access to that can impersonate you, right? Any developer who has access to that database or anybody that steals that database can then pretend to be you. So that's where, hey, this is a start, but oftentimes we need to add additional credentials and more specifically additional factors to really make our authentication secure. So in general, using 2 factors is a lot more secure than just using 1 factor. So if we add more credentials, but they're all from the same factor, they're all just knowledge questions, we really don't get a whole lot of security. If somebody has access to your records, and they know where you were born and the cars that you've had and things like that, especially from like a government agency point, adding additional knowledge checks doesn't really add much security because they know everything about you. So somebody that's trying to steal your identity, they potentially may have a lot of knowledge. So adding additional things doesn't give you much security. Similarly, if we're looking at biometrics, let's say I ask for a fingerprint. Does asking also for a retina scan add much security?
No.
Not really. Because if I'm in a place where I can get your fingerprint, I'm also probably in a place where I can get other biometric information, right? So I generally have to be in close proximity. You have to be potentially in the room with them at some point to usually get their biometric information. But let's say, as they do in the movies, you knock the guy out. Well, you have his hand and his eyes. Right? So if that's all you need, you knock the guy out and you have both of those credentials, right?
Yeah.
So if you want your secure secret base your secret layer to be secure, you don't just ask for a fingerprint and retina scan. You ask for the PIN code that he can't tell you because he's knocked out. So additional factors really enhance that security. So just going from 1 factor to 2 factor drastically increases your security. If you go then further, say to 3 factors is much more secure, right? Every factor you add adds a significant amount of security. However, you have to realize that every factor you add also makes it harder to get in and makes it potentially less usable. Right, so I could say, well, let's go over all 5 factors, but then we would have a lot of cases where, well, the user gets into a problem because, well, if they have to prove their face, well, what if they're wearing a hat, as you were saying, right? Or what if they're wearing glasses instead, or there's something different about them that day where they can't meet that check. So generally, we don't do all. But 2 factors is still better than 1, which is kind of your default. And that's why a lot of companies, especially game companies, say, and your banks say, please, 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 please add a second factor because it will make it a lot more secure. So usually most websites are generally what they mean by 2 factor. It's really just knowledge plus possession. Does that make sense? Usually that's the 2 factors that we're talking about. But it doesn't have to be. So, and especially it's worth considering that because possession isn't, especially if you're using, a phone number as part of that possession, that can be exploited. So sometimes other factors are things you want to consider. Okay, so we're talking about factors. So we want to kind of work down, we've kind of talked about a lot of theory at this point. I want to start working down towards how do we actually put this authentication system into practice. So what we need to talk about now is something called cookies. Cookies are something that's built into the HTTP protocol itself. It's there. I'm sure you've heard the term at some point. But it's a key piece in really implementing almost any authentication system. You can implement authentication systems without cookies, but there's a lot of value that they provide in increasing security as well as potentially implementing things that you couldn't do without cookies. So a little bit of backdrop on HTTP before we get into cookies and what they are and how to use them. One thing you need to understand about the HTTP protocol is that it is stateless. It's formally defined to be stateless. And that's actually really, really fundamental to the web and how it works. Other protocols that came before HTTP, most of them were not stateless. Stateless is kind of an unusual thing. So for instance, if you think about sending emails, if you're sending emails, the historic protocol for that are things like SMTP or POP. Both of those are stateful protocols. And the way you can kind of think about that, let's say they kind of work like a command line where you tell them to do something and then you tell them to do something and then you tell them to do something. But that command line or that connection has a state to it. So for instance, I can't do anything with my email until I've logged in, right? So I have to prove my credentials and then maybe start drafting an email and then I can send it. Or maybe in the process I have to add people I'm going to send it to before I can send it, right? So there's an order to all of the operations, and if you do things out of order, then it breaks, right? So, but that doesn't exist with HTTP. You can issue the requests in any order you want, and the whole point is that the server doesn't remember you. That's one of the big things about HTTP is the server doesn't remember you. If you say, I come to the website today and then I come back a week later, that week later it has no idea. It doesn't remember. In fact, it's so low level that let's say I refresh the page. Well, the server doesn't remember that you asked for it previously. Or if I go from the home page to the login screen, the server doesn't remember that you were previously at the home page. Nor does it require you to have to go to the home page before you can go to the login screen, right? So I can visit the pages out of order. That's important, right? Or I can try to go to the dashboard before I've even, right away, with skipping your home page, skipping your login screen, right? You saw that with the emoji application, right? If I just type in /dashboard, I'm at the dashboard.
So it's dumb.
It's sort of dumb. But the upside of that is that it means that every request and response cycle, each of those, can be treated completely independently. And that they're completely self-contained. It means the server doesn't have to look up information about a previous request to go fill the current one. So this means that your requests can be processed at the same time. They can be processed in parallel, and they can be processed in any order, right? So if 10 people are using your website, they don't all have to be processed in the same order that they came in, right? If your state matters, then that might matter. Then you might not be able to do that. So we can process in any order. And with all of this, it means that HTTP is really fast. And in some case, it's what I would say simple. Maybe not dumb, but simple, right? It's a simple protocol. So the fact that HTTP is stateless really matters a lot, and it's something we don't really want to violate because it provides those benefits. So overall, the fact that it's stateless really gives us good performance. It makes it easy to handle errors because when you say an error, well, that's just an error in response to the request that was just sent, and it doesn't affect any of the other requests. If I had a stateful protocol, then maybe I issue one command and then it fails. Well, maybe all the commands from there on out fail, right? So that would mean all my requests from there on out, they fail. I have to disconnect from the server and start over, right? That would be potentially a problem. So it makes it good for error handling in the sense that your errors are handled exclusively and related to a single request. And it also means that things are a lot easier to test because I can replay that request, right? I can say, here are all the inputs for this request. Let's just try that again, right? So if there's no state, if I issue the request again, I should get the same result, right? Now, I say that HTTP is stateless, right? So that means that, for instance, if I go to your dashboard or your login screen and it doesn't really remember things, I can refresh that page and get the same result. Or I can try the same login credentials and get the same result. But let's say I'm inserting a product into my database, right? So I call your REST API to insert a product. Can I replay that request?
Yes.
I can definitely try it again, and all I need to know is about the parameters that went into that request. I can do it again, but what happens if the previous one succeeded? Are those two inserts going to give me the same results?
It depends on what your primary keys are, I suppose.
Depends a little bit, right? Yeah. So let's say my product name's not unique, right? And so I insert a teddy bear, and then I insert a teddy bear again, right? Am I going to get the same result from both of those inserts?
No. Wouldn't the IDs be different?
The IDs would be different, right? Well, but I just said that HTTP is stateless. Is that been violated because those two requests gave different responses? Even though I gave them the same inputs? Right? If all the product information was the same from the first product to the second product, right, then the request is the same, but the response is different. Does that break the fact that HTTP is stateless? Yay.
No.
Why not?
I mean, I don't know how to explain it, but I couldn't see that as a state exactly.
Okay. So state is kind of monitoring, it's some data, right? So in general, is there data that's being changed or viewed, right? So if I insert a product, right, that does change some data, right? Where is that data, though?
On a database.
It's in the database, right? Well, the database is not part of HTTP. Does that follow?
Yeah.
So as far as HTTP concerned, it's stateless. It's the transport protocol. It doesn't know that your application is maybe using a database to store state, right? So obviously the database has state. And it's used to store state. But that's kind of irregardless of the HTTP protocol. That's a separate piece, right? So we can have state and work with state even though the protocol itself is stateless. But we largely have to have, in order to have state, we have to have things that are kind of outside of strictly the HTTP protocol. So for instance, if I have a database, that's kind of outside of that restriction. So that being said, while we do get these benefits from HTTP being stateless, it does make it a little bit harder to do things like users, logins, and authorizations, because I can't require the user to have to go through the login screen first before they go visit the dashboard page. Does that make sense? I can't require the user to do those operations in a certain order. Cool?
Yep.
So how do I track that? So one of the tricks that we use is something called a cookie. Cookies are a way to make your apps, which normally would be stateless, stateful. And as it turns out, cookies are part of the HTTP protocol in some way, shape, or form. It's just kind of odd that they, as it turns out, they don't violate that state rule. And part of that has to do with that the state is stored on the client and not stored on the server. And it's not really connection. It's not part of the connection. It's part of a different storage mechanism. So a cookie is a little bit of data that's stored on the client side. And generally we store it, it's going to be stored on the client side in a file. So if you were to look into your web browser files, you would find that you have all these little your web browser directories. You would find that there's all these little temporary little files called cookies. And each cookie contains a single key value pair. So I might say, like, your theme is dark, or your language is English. Those would be stored in cookies.
Yeah. Quick question. Why that name? Why cookie? Is it like after the dessert, the little, like an actual cookie? Why that name?
That's before my time. I don't know how that name originated, but we've been using it since, I think, the 80s, if not earlier. But I think that name stems back to the 80s.
That explains why they named it Cookie.
So it's a bite-sized piece of information. I think that's basically what it gets down to. It's a small piece of information. So there's the most important thing to remember is that they're stored on the client side. The server does not store your cookies. Okay, they're always stored in your browser. Things that means is if you delete your cookies on your browser, they're gone. They only exist on your browser. Also, things to consider because they're stored on the browser. Let's say I switch from Internet Explorer to Firefox or to Chrome, right? Do those all have the same cookies? Do they share cookies?
No.
They don't, right? Because it's a different browser, right? Or let's say even I have the same browser, but I have my browser on my laptop and I have my Chrome browser on my phone. Do those share cookies? Well, they don't because it's stored on the client side. Okay?
Doesn't Chrome have an option where you can share them, like synchronize them?
You can synchronize certain things. I don't believe it's synchronize cookies still. I think cookies are still one of those things that doesn't synchronize, but it does synchronize a lot of things.
Okay.
So that's one thing to keep in mind. Generally, that doesn't happen. There's no saying that a browser couldn't decide or Chrome couldn't decide to do that if they haven't done it already. But I believe those are still separate because generally speaking, if I log into a website, I don't usually have that same login on my smartphone. I usually have to log in again. Say I log into Facebook on my phone, that usually doesn't mean that I'm logged into Facebook on my my laptop. I usually have to log in both places, which to me indicates that the cookies are still separate.
Yeah.
It's worth noting that the cookies, once they're issued, the server generally does the issuing, but they can be created on either side. Your JavaScript code can work with, read, and create cookies, but your server can also do it. Generally, though, we do it on the server side. Once that cookie's been issued, every request from there on out, your browser will send all those cookies back. So let's say we issue 3 cookies. Every time now the browser asks for a page on that website, whether it be a CSS file, a JavaScript file, an image, a video file, anything it asks for, it's going to send all those cookies back to the server every time. Okay? And that's worth noting because it does mean that if you put a lot of data in your cookies, it's going to slow the website down. Because every time you ask for something, you have to send all the cookies. So if I say put a megabyte of cookies, right, on your computer, every time you ask for my website, you're going to have to send me that megabyte of cookies. Can you understand why that might be a problem?
Yeah.
Well, I use up a lot of mobile data.
Yeah. A lot of mobile data. You'll notice that every page, every image, every CSS file loads slower now. So we want to make sure that whatever we put in the cookie is small. It should be a cookie, a small bit of information. If we violate that, then we're going to get into trouble. It's worth noting also that those cookies are always stored as plain text. There's no encryption on a cookie. You give it to the computer and it's just stored on the computer completely unencrypted. So if you say have that cookie store the user's password, right, then anybody who has access to that computer can go get the password out of that cookie file. Not only do we want to make sure that the cookies are small because of performance, we also need to make sure that the cookies don't store sensitive information. So they can only store information that you'd kind of be okay if somebody read it. Okay. On a similar note to that, it's worth noting, I think I said this already, is that your cookies are both readable and modifiable from your front-end JavaScript as well as your back-end JavaScript code. Both the front-end and the back-end can read your cookies. Okay, so what's in there is really, in a lot of ways, not private. So if it's something you need to have private and not leaked, such as the actual password, that should only be something that exists in the database. It should never exist in a cookie. So things that means like normally on the login screen, let's say your login screen provides the username and the password. That's what you type in. Well, if I'm then going to use a cookie later to prove your identity, I can't use that username and password. I can't just put that into the cookie. I could implement it that way, but it would not be secure. So I have to put something else into the cookie, right? So what else could I put into the cookie to prove your identity?
When I did it, I just did the ID. So like their database ID.
So that would be one way to do it. You could just put their user ID in there. And it turns out their user ID is usually pretty easy to get, so that's not a big risk from privacy. But then you basically use that user ID to prove who you are from there. Now, out of the box, you have to recognize that that maybe isn't secure, because you can change. I can edit my cookies. In fact, not only can you do it from code, but there's an extension for most browsers. You may, if you're not using Chrome, you may have to go look up a different extension. But I use a extension on my browser called Edit This Cookie, which lets me get easy access to any of the cookies in my browser. So if I want to look at a cookie, I've got a little icon up here. It looks like a cookie, and I can click on that, and that will show me the cookies I have and the data that's in there. So that provides a very quick way to go see what the cookies you have that are currently being used for the website, and then go edit them. It lets you delete them as well, change the expiration date, and manipulate them. So this is a very good tool as you're working with these authentication systems to be able to go mess around with your cookies and see that things work and see that things are still secure. So cookies always come with a small set of properties. They always have a domain name, which is kind of who issued the cookie, what website issued the cookie, who does it belong to. So for instance, if you're on the Ranken website, and actually that's probably a good one to check cookies on. So if I go to the Ranken website and I click, I have a few different cookies, right? So Ranken has given me 1, 2, 3, 4, 5 different cookies. See that?
Yeah.
So I can see in there the first thing that's issued is it's issued by Ranken edu. So that's the domain. I can see the name of this cookie is kind of a little bit obtuse. It's __ CFDWID. And what's actually in there, I'm not entirely sure, but that's what they have as the name of the cookie. You have the value here, which looks like it might be a GUID to me of some sort. You've also got when it expires, right? So this cookie expires on the 14th of November.
And that expiration date's set by the browser, right?
That's set by the server generally.
Oh, the server?
Yeah, because generally the server is the one that gives you the cookie. If you're doing it on back-end JavaScript, you're going to be setting the time from the back end. If you set the cookie from the front end, then you're setting the time on the front end.
Is it reset automatically, or does it wait till it expires then resets it? Like you just visited the page now, so if you would have somehow checked that before, would it have been different, or does it wait till November 14th and
so
do it
I
again?
can do an easy check if I just refresh the page. It looks like that cookie is still the same expiration date, right?
Oh, okay.
Now, if I were to delete the cookie, which I can click up here and delete all the cookies are all gone. Once I refresh that page, I'm probably going to see a new cookie, which I did, which expires now at November 25th. So the website said, "Oh, you don't have that cookie. Let's give you a new cookie." So basically, when the cookie expires, it's deleted. That's what happens. When the cookie expires, it's deleted. So then the server can detect that cookie doesn't exist. Does that follow?
Yeah, I see that. It looks like it did it for 30 days.
Yeah. So yeah, 30 days from wherever I visited, roughly. So when you're creating your cookie, you have to set those things. You need to know what domain name is it for, when is it going to expire, what's the name of the cookie, and what's the value of the cookie. Now, oftentimes you can get away with not setting the domain name because automatically it will pick the domain name as whatever website you're on. So for instance, I'm on Ranken edu, it kind of knows that, so it can fill in that data. So with Express, as it turns out, we actually don't have to specify the domain name. That generally happens automatically for us. So let's go through some code examples of how to work with cookies. With Express provides a few different methods to read cookies as well as to modify them. So if you want to set a cookie, what you do is you use the response object and you call the cookie method. So res.cookie sets a cookie. It creates a cookie or replaces a cookie if there's already one there. So to call this method, I need to provide a name and a value for the cookie. I can also provide some additional options, but those optionals are optional. I don't have to provide additional options. I can just say, here's the name and here's the value. So if I do that, then I'm saying, well, let's define a cookie with the name theme and the value dark. So here I'm setting the theme to dark, basically. So here I'm going to say, well, let's set a cookie. So this will create a cookie that'll be sent back to the browser, and the browser will save it. That's all I've got to do with Express is res.cookie. Cookie's been created. The additional options that you can provide, there's a lot. There's actually a bigger table than this if you look at the documentation, which I've linked here. But these are really the only 4 you need to know about. One option that you can set is the domain, and that's the domain name for the cookie. By default, it actually defaults the domain name of your app, so typically you don't need to set it. The place where you might want to set the domain name is if you have a website that crosses or is available on multiple domains. That's where you would want to set the domain name. Or things where you maybe have a subdomain. For instance, if you are deploying things on Heroku, you might want to not have it as herokuapp.com because that would be every Heroku app. You might say my Heroku app, my thing, my portfolio, Paul's portfolio dot herokuapp.com is the domain. So in general, it will default to those things, but sometimes, especially if you're using subdomains or different domains, then you may need to set that yourself. The next thing you can set is the expires property. The expires property is always a date, and it says when does that cookie expire in terms of GMT. If you don't specify an expiration date, or you set it to 0, then the cookie expires when the browser session ends. So whenever you close the browser, that cookie will be deleted if you don't specify an expiration date. So it's what we would call a session cookie. Okay, so that's your browser session. Now that you can set the expiration date that way directly, but it means you have to do some math to say I want it to be 5 hours in the future, etc., which can get a little bit quirky. So oftentimes what we'll do instead is we'll use the max age property. These are mutually exclusive. You can't set both expires and max age. It's one or the other. But if I set the max age is a number, and it just says how many milliseconds from now do you want it to expire, right? So if I wanted it to expire in a minute, I would say it's 60,000 milliseconds from now. So let's say I want to issue a cookie for 24 hours. What would I need to set the maximum age to? Well, I need to set it to 1,000 times 60 for minutes times 60 for hours times 24. So 1,000 times 60 times 60 times 24 would be 24 hours. And generally you want to write it out with that multiplication in there. Don't go through a calculator and pre-figure out the calculation. Just put the calculation there, because otherwise it's a lot harder to read. And as it turns out, doing the calculation beforehand doesn't actually provide any performance benefit.
What was it again? One more time.
If you're putting a calculation there for the number of milliseconds, just put the calculation there with the multiplication and division if you need it. Don't go through a calculator and say, okay, this is 25,000 milliseconds, right?
Yeah.
Because that's very hard to read and very hard to figure out how long it is, and then harder to go modify the code later. A lot of new developers think, well, that multiplying it out saves some performance cycles. It'll make it go faster. As it turns out, it doesn't. It doesn't make it any faster to write it, to do the multiplication ahead of time, because the compiler that runs it already does it. Already will do the calculation ahead of time for you, even if you write it out as a multiplication. So if you're setting the match size, I want to see those multiplications. The last one that you might care about is the secure flag, which is true or false. And that, I think by default, is false, but it marks the cookie as being HTTPS only. So if you mark it as secure, then it will only send that cookie back and forth as long as you're on an HTTPS connection. Otherwise, it'll send the cookie back potentially in plain text when you're using an HTTP connection. So those are the options that you can provide. Again, there are more options. Those are really the only 4 you care about in general. The other ones are for more edge cases that you're probably not going to run into at this point. So you can read about what those are, but I don't really think you'll need them. So the cookie method on the response object will let us set a cookie. Sometimes we need to delete a cookie, say you're logging out. So to delete a cookie, you call clear cookie. But to clear a cookie, all you have to do is just provide the name. There's no additional value or options. You just say, well, what's the name of the cookie you want to delete? So you want to say, okay, well, they've decided to go back to the default theme, so clear cookie theme. Oftentimes you'll see this when you log out. Typically when you log out, you want to clear their cookie that keeps track of them being logged in. So given that, I could do a very simple authentication mechanism with a cookie where I just say, well, let's say the name of the cookie is user ID, and I set it to your user ID. So when you log in, I save your user ID into a cookie. So if I do that, then I can handle as many users as I want. Because that data is stored on the client side, I'm not limited to, like, I can only have one user, right? Put it in the cookie. Do I have to keep track of who's logged in? Nope, I don't. I'm just tracking it by those cookies. Now, what might be a downside to maybe storing it that way? If I say the way we're going to track that you're logged in is user ID and set that user ID to 5, well, how is that exploitable?
You could just change your user ID.
I could just change my user ID. So let's say, Troy, your user ID is 11. I go into my cookie and change it to 11. Am I now acting as you?
Yeah.
Yeah, that would be a problem, right? So out of the box, they are not secure. They're in plain text and they're easily modifiable, so they're not secure. But they are still an important part of making a secure system because it gives us a way to store data on the client. So I can set a cookie with cookie. I can clear the cookie. I can also read the cookie. Now it's worth noting that when I set the cookie or delete it, I'm setting it on the response. But when I want to read the cookie, it's on the request. You hear that?
Yeah.
So you modify the cookie on the response, but you read it on the request. So request.cookies is a property of the request object. It's actually an array, or sorry, it's an object. Cookies is an object, and then you can refer to that by the name of the cookie. So if I want to get the theme that we had set earlier, I would say request.cookies.theme. So that'll give me that theme cookie that we set previously. And oftentimes when I'm reading a cookie, I need to have a fallback. So I might say, well, if you don't have that cookie, then we'll default it to light. We'll use light instead. If you haven't set your preferred theme. So similar things like if I was having a user ID, I might say, well, if there's no user ID cookie, I might set this to null as my default value. So if there are no cookies, it's worth noting that this object defaults to just an empty object, just curly braces. So that object will always be there. Request.cookies should never be null, but it may or may not have that property, especially if that maybe you set the theme cookie but it expired. Well, then that theme cookie is not going to be there anymore. So don't assume that the cookie is there. You should always, if you're reading a cookie, you should always check if it has a value. Cool? Because that cookie could easily be deleted or expired. So some pros of using cookies: they're stored on your client machine. They're really good for application-wide state because they're sent with every request, so we can read them every time. You do your login screen, and then from everywhere there on out, we can go read that value. But cons for them is they're not secure by themselves, because users can view and edit them through extensions and the like. They can also be hijacked by XSS attacks. Remember we talked about cross-site scripting attacks? Problem there is that they're readable and modifiable from JavaScript. So if I'm able to, say, post a comment on your website or a review of some sort, and that includes JavaScript, then I can run some JavaScript to steal your whatever's in your cookies. Does that follow? Or if you allow the user to put JavaScript in there, I could potentially change your theme to dark theme without your permission, right? So you do have to be wary of XSS attacks when you're thinking about these authentication mechanisms, and especially the cookies in particular. As I mentioned in a previous kind of slide, I did say, if you have large cookies, they're going to slow down your user experience because they're sent with every request. And I mean every request, not just to your REST APIs, not just to your routes, but to everything they ask for, including image files and video files and such. So what that means is we always want to keep the amount of data that we're storing in cookies really low. 1 megabyte is huge. And even a kilobyte is a lot when you're talking about cookies. Okay? So things that you probably shouldn't store in cookies. Let's say I've got a profile image, right? Should I store that in a cookie?
No.
Probably not. Should I take my entire user object and store that in a cookie?
No.
Probably not. A, because you might have some big data in there, and B, because, well, you have a password or other private information in there, right? So you don't take an entire database table and stuff it, the entire user object or a database table, and stuff it in a cookie. That'd be bad. So anytime you're creating a cookie, you should pick and choose what the data is that you actually need to store. And it should be a very small amount of data. In reality, you should probably write that down somewhere in some of your documentation and say, hey, here's the names of the cookies and what they can have. And if that list grows bigger than 5, then you might need to reconsider.
So what would be some other examples that would be used? We wouldn't want to store user data. It would be theme and maybe language.
Theme and language are both great things for that, because that's an application-wide setting. If I'm looking at documentation for things, for instance, if I'm looking at the Android documentation, you can write Android in either Java or Kotlin, so they store the language of the code examples in a cookie. Or if you're at the .NET documentation, they give it code examples in VB or in C#, so that's also stored, things like that. In addition to maybe like the version of the documentation that you're looking at, those kind of things are stored in cookies with the .NET documentation. So are you looking at .NET 4.5 or .NET 3.5 because the documentation is different? So you can see a lot of things like that, especially when you're dealing with documentation. But for most websites, it's usually there's a token that's used for authentication, which we'll talk about for your login. There might be a cookie for your theme. There might be a cookie for your language. You might have a cookie for your time zone. So you can set your time zone across the website. Those are kind of common things. Okay. Let's go ahead and take a break. It's around 2:20 right now, and we'll come back at 2:40. So let's take a 20-minute break, come back at 2:40 so everybody can have a chance to stretch their legs. So to recap what we've talked about so far, so we've talked about what authentication is. Authentication in general is any process that you use to prove your identity. Typically, when you initially go to maybe the login screen, the way you prove your identity is with your username and password. We talked about some other ways, tools that you can use for that, but that's pretty much what it's going to look like for our applications, is a username and password. Okay. Now, once we get past the login screen, typically we don't really ask the user for their username and password again, right?
Right.
We might ask for it later if you're doing something like trying to change your password for security there, but typically we don't ask for it again until you log out. Well, then how do we keep track of the fact that you logged in, right? Well, we use that cookie, right? Because HTTP is stateless, we use cookies to remember that you're logged in, okay? And we're typically going to send some sort of expiration date there so that you don't say logged in for forever, right? So it automatically deletes itself. So typically when you log in, you're going to provide the username and password, and then from there we're going to authenticate you using cookies instead of a username and password. Okay? So every time you ask for a page that requires you to be logged in, we'll check your cookies and see if they're valid. And if they're valid, then you'll get to see the page. Otherwise, basically, we'll kick you back to the login screen. Does that follow?
Yep.
That's our goal.
So are we using kind of like a validation then?
Sort of. We're doing validation on those cookies.
Okay.
But not using the validation mechanisms that you've kind of learned. Like I wouldn't use necessarily Joy for that, and I wouldn't use like Bootstrap Val. You might use some if statements, but I wouldn't use Joy or other things like that. Okay. So you need a few new tools potentially to kind of deal with that. With what we know already, okay, we know we can write cookies and we can store the user ID in a cookie, but that data is still modifiable by your end user. Your end user can go in and change their cookie at will. They can read it. There's no hiding it. So those may be things that we need to correct, right? So the next kind of topic is the next steps of topics is starting to think about how can you make that cookie secure. So we can set the cookie, and the cookie API, as you saw, is really simple. It's 2 methods and 1 property. That's it. So actually working with cookies, I think Troy, you said this in Discord channel. It's actually really easy. It just becomes a question of then how do you build on top of that and make it secure. Okay. So what could I do to make that cookie more secure? To prevent the user from being able to edit it or to manipulate it in some way. What could I do? Or to make sure that people can't steal your cookie.
How about HTTPS?
Okay, that's one part of it. Yes. Why would HTTPS help?
Well, I just know it's secure. I don't know the technical aspect of it.
Okay. The S actually, some people say secure, some people say it stands for SSL. In general, the thing to understand about HTTPS is that it is encrypted. So HTTP is not encrypted, HTTPS is encrypted. So encryption is a big part of how do we make these things work. And encryption actually is going to solve a number of problems for us that we have right now with our login systems. So let's talk about what encryption is. Okay. So encryption is a method by which information is converted into a secret code that hides the information's true meaning. So in general, when we're working with encryption, we're kind of talking about codes, and encryption and codes have been around for a long time. We can go back to the Roman Empire and see that they had something called a Caesar cipher that they used to encrypt their messages, which was, as it turns out, a really simple cipher. But the point is that ciphers have been around for thousands of years at this point. They're not a new concept, but the way that we do encryption with computers has changed a little bit. So when we're in computing, we talk about unencrypted data. That's generally known as plain text, and encrypted data we generally call ciphertext. So you have the plain text, which you can read directly, or the ciphertext, which is basically unreadable because it's been run through a cipher. So the formulas that we use to encode and decode messages are generally called encryption algorithms or ciphers. We use either word. So you take your plain text, you run it through a cipher, you get your ciphertext. Who can think of maybe what would be a simple encryption algorithm that you maybe run into at some point? Maybe even in like grade school.
What were the decoder rings that came in the
ring
boxes?
Yeah, that was what we call a substitution cipher. It's actually very similar to the Caesar cipher. It's a little bit more sophisticated than the Caesar cipher, but it's based on that. What else?
I mean, if they're mixing stuff up, I guess, would like an I test kind of run into that if they're doing like different, if it's like an I, but there could be a 1 there instead.
Mm-hmm. I think that falls into more the kind of, it's a little bit closer to the leet speak thing they were talking about in the, Linus was talking about. I know this is, they used to have these puzzles in newspapers a lot of times, and sometimes you'll see them in back of cereal boxes as well. Sometimes you'll see like a bunch of kind of scrambled letters, and they'll tell you like, figure out what the message is. And as it turns out, basically it's things like every A is an E and every P is a Q, or things like that, right? Where each of the letters you substitute with another letter, right? So we'd call that a substitution cipher. You seen any of those before? Maybe?
I've seen them, yeah. But
Yeah.
So substitution ciphers are kind of your basic, simplest version of ciphers, at least one of the simplest ciphers. They're not terribly secure because they're actually pretty easy to guess, but they are the basis for a lot of more complicated ciphers, are kind of built on top of that basic idea, where you take one letter and replace it with a different letter. You might have heard of the German, the Enigma machine, the Enigma code.
yeah.
It was still kind of a variant of a substitution cipher. Basically what they would do is they'd push this key on a keyboard, and then it would, instead of printing the key that they typed, it would print a different key. The catch with that was that there was a bunch of wiring about how that was changed, and it actually depended on all the keys that you'd typed before. So you could type a bunch of Qs, and it wouldn't be XX. It wouldn't be just a bunch of X's. It wouldn't be the same letter every time. It would change because it had some internal state. So that's part of how we make things better, is building on some of those ideas where you have state built into the cipher, where every thing that you encode changes the state of the cipher. So the next thing, even if you encode the same thing, it encodes differently. So in general, though, to be effective, most ciphers include a variable that's used as part of the algorithm. That variable is generally known as a key, and that's what makes the cipher's output sort of unique. So if you use a different key, then you get a different output from the encryption algorithm, or you encode and you decode differently. In general, so when an encrypted message is intercepted, say I'm sitting on your Wi-Fi network and I can see all the data you're sending back and forth in HTTP, well then I can see those packets, I can read that data. If that data is then encrypted, I can't just read it directly. I have to guess both at the cipher algorithm, the cipher that you're using, whatever the algorithm is, as well as the keys that you've selected, in order to be able to decrypt or read that message. And that additional time and difficulty that it takes to guess the key or figure out the cipher algorithm, specifically usually the key, that is really what makes it valuable, is that it slows down the amount of time that it takes to read the data, and oftentimes ideally slows it down to the point where it's no longer practical or the data is no longer useful at that point. So for instance, let's say we have a token that proves that you can log in, who proves who you are, right? Well, that may take, if that token is good for a day, but it takes you a week to decipher it, well then that's fine, right? Because by the time you finish deciphering it, it won't be any good. Does that make sense? So as long as as long as the encryption is good enough to, you can have stronger encryption or weaker encryption. The stronger encryption it is, in theory, the longer it'll take to decrypt it. So there are a few different kinds of encryption. It basically you can boil down pretty much all encryption into one of three, pretty much, at least simple algorithms. into either symmetric, asymmetric, or hashes. So a symmetric encryption algorithm just uses one key. It uses one key to encrypt, and it uses the same key to decrypt. So if I have the key, I can both turn it into ciphertext, but I can also read any ciphertext. Okay, so that's your basic encryption algorithm. So like a substitution where you're saying every P is a Q, and things like that, or Pig Latin, right? You add some letters to it. I just need to know to remove those. That uses the same key to encrypt and decrypt, right? So generally with symmetric ciphers, you can just run the same process in reverse and get back the plain text. Does that follow?
Yep.
Okay. Asymmetric is where the process for encrypting is different than the process for decrypting. And in general, you need one key to encrypt and one key to decrypt. So if you only have one of those two keys, you can only do one of those two things. But if you have both of those keys, then you can do both the encryption and the decryption. Okay, and generally we refer to these type of algorithms, asymmetric encryption algorithms, as public-private key algorithms, because usually what we do is we have one of those keys be private and the other one be public. So everybody basically, we let one of those keys go out in the public and anybody can use it, and we use another one, and the other one of those keys we keep to ourselves as a secret. So that way, for instance, if we say everybody gets the key to encrypt, then anybody can encrypt, but only we can decrypt. Or you could do it the other way around, and where we say we are the only ones that can encrypt, but everybody can decrypt the message that we sent. So you can do it both ways. But the catch there is that the keys are different. You have two keys instead of one key. And generally those keys are just really, really big prime numbers, is the kind of things that we usually choose as those keys. So the problem kind of becomes to factor those prime numbers if you want to get back to the original data. Factor the numbers. Where was I going here? So you'll see that this idea of public-private keys in a lot of places, because it's a trick that we use for most encryption across the web nowadays. And it's not the only thing we do, but it's one tool. Another sort of encryption, it's not really generally categorized as an encryption algorithm, is what we call a hashing algorithm or a hashing function. And a hashing function is one way. So encryption, symmetric, asymmetric, is always two ways. You can encrypt it, but you can also decrypt it to get back to the original value. Hashing only goes one direction. You take the plain text, you take the value, you hash it, and now you have a hash, which effectively is sort of a random number that comes out of that input. If you've ever heard the term checksum, checksum is a kind of hash. So the idea is that if you change the input, you get a different hash. But you can't go from the hash back to the original input is the goal. Cool?
How would you get it then? What would be the point of just encrypting it without it ever being able to decrypt it?
This actually gets used quite a bit. So things like, for instance, let's say I want to take this is actually really good for things like passwords. So if I want to, if I say, you give me your password as Pony, right? That will give me a hash, right? If you then come back later, tomorrow, and give me the password Pony, I can run that hash string algorithm again, and I should get the same outcome tomorrow. Does that follow?
Oh, okay, yeah.
So I can rerun it because it always, the idea with the hash is if you have an input, you always get the same output. So I can take, your password on 2 different days, run the hash, and compare them, which means that I don't actually have to save your password. I just have to remember the hash of your password.
Oh, all right. So you kind of have to know what it means.
Yeah. You have to know what the hash means.
Well, like, if my password's 1, 2, 3, 4, 5, that's going to create a hash, right? I know that because I see it happen right before me, but nobody can figure that out. But it does produce, I don't know what I'm trying to say, but
the idea is that nobody can take the hash that you got out of that and figure out that it was password 1, 2, 3, 4. That's the goal.
Okay.
Is you want to say, looking at the hash, I can't figure out what the original value was. That's a goal with a good hash.
Okay.
So if you can go from one back to the other, then it's not a good hash. So it's good for that. It's also good for things where oftentimes we'll use hashing to find out if there was errors in transmission. So for instance, let's say I send some data to the server, including my maybe it's my credit card number and stuff like that, and I want to make sure that it got to the credit card number, got to the server exactly how I sent it. So I might hash that data and then check that the hash is the same when it gets there. Because if it's not the same, then I know the data didn't get there whole. Something happened to it. Does that make sense?
Okay. I guess I'm thinking like if it got saved elsewhere, how would it be usable again? I get that it's encrypted, but picking up on that part, maybe some examples.
The catch with the hash is you strictly use it to compare A with B. That's all you use it for. Is you say, is A the same as B?
Okay. Yeah, I see it. That I get it now. Okay, yeah. That helps.
You just run the hashing algorithm again and see if you get the same result. And that way if you get the same result, in theory you have the same input. If you get a different result, then you definitely know that you have a different input. With hashing, it's worth noting that you can get the same result from multiple inputs. So for instance, if my hash algorithm is to give me a number and take the modulus 100, well then if you give me 10, right, modulus 100, that's 10, but if you give me 2010, well that still gives me 10. So if I run through my modulus, if my hashing function is just take the number and do modulus 10, actually that would be 0. I would get modulus 0 from that. If I do modulus 10, then I would say, well, both of those 10 and 2000 both give me the same hash of 0. So they're the same password, right? Because they give me the same hash. So you have to be a little bit careful with that. Cool.
Yeah.
So that's what we refer to as a hash collision, where 2 different inputs give you the same output. If you're using a hash that's designed for working with passwords, generally it's built in such a way to make those hashes really rare enough that they're not easy to manufacture. But they can still happen. So in reality, just because they have the same hash doesn't actually technically mean for sure that the original input, but the odds that they're not the same should be so low that you can treat them as if that's always the case. So a few different places that you'll see encryption used, and problems that we want to solve here in the next 2 weeks. And look at. First one is that we use encryption for the protocol, to encrypt our protocol, to encrypt all the traffic that's going to the server and back. And we do that by running our data through HTTPS instead of directly through HTTP. So HTTPS means that we add this SSL layer on top, and that provides some encryption. Okay. And specifically, when we're doing encryption with HTTP, I believe that there's a combination of some asymmetric encryption as well as some symmetric encryption that facilitates this. When we're dealing with passwords, we'll do some hashing because basically when we store the password in the database, we don't really want to store the original password because the problem is if I store the original password in the database, anybody who has access to that database can figure out what that password is, right? They can just read it. And I don't want to do that. I don't even want to trust my own developers, my own employees to see my customers' passwords, right? Does that follow?
Yeah.
So you never want to store the raw password actually in the database. I know we've done that kind of already as kind of as a sort of workaround, as a quick way to implement it, but it's really something we want to not do. So what we'll do instead of storing the password in plain text, we'll store a hash of it in the database. So that hash will look like garbage, but we can still use it to verify that the password is correct. Another place where we'll see encryption come in is with authentication tokens, which will use something called JWT to implement that. And in fact, that's what we're working towards, and this is what we're going to use to store in the cookie. We'll store a JWT token, which provides a lot of extra security measures for that cookie that otherwise wouldn't be there. Cool? So let's talk about HTTPS. So the HTTP protocol, as I've mentioned a few times before, doesn't provide any encryption out of the box. It's completely unencrypted. There's no mechanism whatsoever in HTTP that has encryption built in. Everything you send back and forth is plain text. So that includes everything in your URL, anything in your post. If you submit a post request, all of that's still in plain text. Any cookies that you're sending back and forth, those are in plain text. Any content that's in the web page, say you put it in a hidden field, even all of that data is back and forth as plain text. And what that means is anybody who can see the traffic that goes back and forth, there's a few ways to do that with the wired network, but it's a lot easier if you've got a wireless network. Basically, if you're on a Wi-Fi network, say I'm at a coffee shop, I've got the password, you have the password, we all have the Wi-Fi password. Well, we can technically read, with the proper software, you can read all of the packets, all of the data that's going back and forth between your computer and the internet. Right? So that would be a problem, right? You go to login form, you type in your username and password, I can see that. Cool? So that data is not encrypted. A lot of people make the mistake, and especially new developers say, well, that data should be encrypted. My password, I typed it in the field, it's hidden. But no, anybody who's looking at the network can see it. And that's as long as you have the Wi-Fi password. So if you're on the Ranken Wi-Fi, you can see other computers on the Ranken Wi-Fi. Even if you're on not just the Ranken guest, you can obviously see it. You can even see it on the Ranken network potentially if you have the right software hooked up. So we really want to avoid HTTP, right? Because there's no encryption. If I'm using HTTP, then anything I do is going to be breached. It's going to have that security hole in it, in that nothing is encrypted. You follow with me?
Yeah.
So if I don't fix that problem, then nothing else I do matters, Nothing else will really add much in the way of security, or in terms of authentication and stuff. So, one of the first things you have to do is you have to make sure that your server is running on HTTPS. So HTTPS provides a layer of encryption on top of HTTP. It's still HTTP protocol underneath, and it basically works exactly the same way, except that it's encrypted. So when your browser connects to your server, it kind of negotiates some encryption keys with the server through kind of a complicated key exchange protocol, which we don't really care here. It basically just kind of happens. But the point is that it ends up being that the connection or the tunnel between the server and your computer ends up being secure. It ends up being encrypted, whereas it wasn't encrypted without HTTPS. So we add in something called SSL, which is short for Secure Sockets Layer, and that's what actually provides the encryption. SSL is kind of a tool that you can use with any protocol. So we use it with HTTP. You can actually use it with any other protocol. So for instance, there is, remember FTP for file transfer protocol? There's also an FTPS or SFTP, which adds a SSL layer around FTP. Similarly with email, we've got the SMTP protocol. I believe there's also a secure version of that also adds SSL. So SSL is kind of a piece that you can tack on to add encryption to any protocol. The way you can know that that's happening with the websites you're browsing, you just look in the address bar. So if you see this in the address bar, that means you're running over HTTP. You see it says not secure. And you can usually click the I and it'll tell you more about that. But if you're running over HTTP, you'll see it say not secure. And if it's over HTTPS and you've got a good cert, then you'll see a green padlock like this and it says secure. You see that?
Yeah.
So that's generally how you can tell from the browser side. Is it an encrypted connection or is it not an encrypted connection? So that's definitely a good thing to check before you log into anywhere. If you're on a login screen and this says not secure, you probably don't want to log in there, right? You probably want to assume that could be compromised, especially if I'm at like a hotel or at Starbucks. I probably don't want to log into anything like that, right? I want to make sure that it has that secure connection. So part of the way that encryption is implemented, that encryption uses public and private keys to do the encryption. We kind of talked about asymmetric encryption and how some of that works briefly. But those keys are stored in certificate files. You can view the certificate file for any website by clicking the address bar. So for instance, if I go to, let's say I just go to Google, and you can see the padlock, right? If I click on the padlock, you'll see it comes up here, connection is secure, and you see how it says certificate valid. It even tells me there's 23 cookies that it's using. So let's hit certificate valid. It'll pop up this window in Windows. So this tells us actually information about the certificate that's being used to encrypt the traffic. So I see a few things in there. I see the certificates being issued to Google.com, right? So they're who can use this certificate. It's valid at Google.com. You'll notice that there's a star before that, so that says any subdomain within Google.com can use that as well. So for instance, like sheets.google.com or drive.google.com or mail.google.com, they can all use that because it's allowed for subdomains. You can see who it was issued by. And if I read that right, I think that's probably issued by Google. um, because there are what we would call a certificate authority. But anyways, that's the certificate authority that signed it, that gave them this. And you can see where it's valid. So it was issued on the 6th in 2020. And then it's good until December 29th, 2020. Right? So every certificate has a range of dates where it's valid. We can look at a little bit more. For instance, if we go down to details, you can see a few more things in there about all the different specs that go into a certificate. One of the things that you have here is the thumbprint. That's the actual encryption key. So that's what we would call the public encryption key that it uses to send data back and forth securely. You'll also see some things in here. So it says like the DNS name and some alternate ones where it's also good, etc. So you can do a lot just from looking into the browser and seeing information about that certificate and seeing who issued it. Yeah, that's what's right. Organization is Google Trust Services. So Google signs its own stuff. So that's what those certificate files kind of look like. Once you open up in Windows, you'll get that dialog like that. Usually they're stored on your computer as CER files, certificate files. That's usually the extension that you see is CER. But there's more than one extension for certificate files. So the certificate files can contain both the public and the private key. Typically, what you're going to see sent to the browser's only going to get that public key. So when I click the address bar, I'm only going to be able to see the public key. Whereas on the server is going to have a certificate file that contains both. Often, it'll contain both the private key and the public key. So it may be that your browser only has one permission. It can only either encrypt or decrypt. I forget which one. I think it can only encrypt, but the server can decrypt and encrypt with that. These certificates are issued and signed by a certificate authority. We call that a CA. They are large companies that have the permission to sign those, or have been approved by the different software manufacturers to say, yes, you can sign certificates and prove identity. So like VeriSign, I'm sure you've seen that name around before. They sign a lot of certificates. Google's now a CA, as you saw, so they can sign certificates as well. If you go through GoDaddy and get a certificate, you'll see what they're signed as. So there's a kind of a small set of companies that are approved CAs, and so if you get a certificate from them, then your computer, your browser in Windows automatically trusts it. Cool?
Yep.
So those signed certs are always issued to registered domains. You can't go buy a cert for localhost, right? Which is where we've been writing our stuff. It's got to be a domain that's actually on the internet. So you could have you could get a cert for Ranken.edu. You could get a cert for paulsmith.com or whatever it may be. But it always is for a domain. So for instance, if you have a customer that has multiple websites, well, they're going to have a cert. Potentially, they're going to have a cert for each domain name to use HTTPS. Understand? Got it? Questions? Those certs typically come with an annual fee. There are some companies that are including that kind of in the cost of other things. So, for instance, actually, if you go to Heroku will actually host your website with HTTPS, but not charge you for the cert, because they're able to use their own cert for for hosting your website if you're using a subdomain, but if you want to go put your own domain name on there, then you'll have to pay for a cert. That cert generally has an annual fee. That kind of varies depending on where you get it from and who you get it from. It has different rates, but I think it's usually in the range of maybe $100 a year, $200 a year for a cert. So that's not something we'll necessarily do here, but just recognize if you want to be using HTTPS with your website, which you absolutely should, that may be an additional fee. Cool? As soon as you have a login screen, if you have a login screen or you have any way to buy anything on your website, you should have HTTPS. Because otherwise your data is completely unencrypted. So that hits pretty much everybody is it's like, okay, yeah, I have some private data I need to be able to send back and forth. I need HTTPS. In terms of testing, you can actually self-sign your own certs. You can create them and sign them with your own computer. That way you can test things and have HTTPS running on your local computer. Those self-signed certificates are obviously free because you're not paying for having it in a database by one of these large companies. But your browser will warn you that your connection is not secure. So it'll allow it to go through, but oftentimes if you're running with a self-signed cert, it'll say, hey, caution, this website is not secure, and you have to kind of click some buttons to go through and pass on with it. There's more than one way to create a cert, specifically a self-signed cert. You can either create one using PowerShell. There's a few PowerShell commands in Windows that you can use to create one. If you want to know how to do that, I've linked a guide here about that. You can also create certificates using OpenSSL, which is platform agnostic, so you can use OpenSSL on Linux and Mac and Windows, but both of these two techniques actually generally generate different kinds of certs. The basic data that they generate is kind of the same because that's been standardized, but the way they generate the files is different and often to the point of incompatibility. So some things need a cert that's been generated by OpenSSL. Other things may need a cert that's been generated through the PowerShell and the Windows tools. So sometimes you have to research a little bit and figure out, well, what kind of cert does this thing need in order to function? Okay. We're not going to cover how to use HTTPS with Express today. I wanted to give you a kind of overview of where it fits into our broader scope, because as I kind of mentioned previously, if you don't have HTTPS, then you don't really have any security. It's that foundation layer that if you don't add it in, then nothing else really matters. But the good news is, as I kind of mentioned previously, if you put it onto Heroku, you actually get HTTPS automatically without having to do anything to your application. Versus if you want to test HTTPS locally, there are some changes that you have to make to the application to use it with Express. Cool? Questions?
Not for me.
Nope, none for me.
So we've talked about how encryption kind of, a little bit of the pieces when it goes to HTTPS. Let's talk about how to hash passwords and some of the stuff there. So there's a library called bcrypt that you can get off of NPM that's meant for hashing passwords. It actually works really, really well. I've been pretty impressed with it. It's super easy to set up. You just say npm-i or npm install bcrypt. That's all you need to do to bring it into your project as a dependency. It includes a few methods as far as its API. The first method that it has is one called gen_salt, and that will generate a salt and then pass it back to the callback function. These are kind of these methods are all asynchronous, and the default method, the default kind of behavior that you'll see is them doing as callbacks, but you can actually also use them. Bcrypt can be used with callbacks. It can be used with promises. It can also be used with the await async syntax. So I'll go over how to use these in both either the callback or the await async async await syntax. I think I'd find the other one more convenient, but I'll kind of show you both.
Okay.
So,
did you say what a salt was?
I haven't yet. So a salt is a common technique that we use when we're hashing passwords. If you just straight up hash a password without a salt, then every time I take in if I take in a password, I always get the same password out. And the problem is with that is it's vulnerable to an exploit called a rainbow table. So rainbow table is where you take all the common passwords, you run them through the hashing algorithm, and then you save that giant database. So you save all the hashes of all the common passwords. The reason why that becomes valuable is then you can just go through, when you see that the hashed version of the password, you can just say, well, okay, run that into the table. Oh, here's the unencrypted, the unhashed version of the password. So that's one of the vulnerabilities of just hashing passwords without a salt. So the idea is you can spend all that time building this huge rainbow table file, and then you don't have to spend all that processing time when you're trying to actually crack the password. Cool? So what a salt is additional random data that we tack on to the password before we hash it. So it's just a random string. So we attach that random string to your password before we hash it, and what that means is because everybody has this random added salt. If, for instance, me and you have the same password, we'll still have a different hash because we had a different salt. Follow? So basically the salt breaks a rainbow table attack. That's what it does. It prevents that. So you can call gen_salt to generate a salt, and then pass that into hash, or you can actually directly call hash and it will take care of the salting part for you. So the hash method has two versions. One version that takes the number of rounds to salt it, how many times it's going to salt it, hash it, salt it, hash it, salt it, hash it. And then a method that if you were generating the salt beforehand, you can say, well, let's pass the salt in here. So you can either call it with a salt or you can call it with a number of rounds. So if you say gen_salt, you're going to then do the second version. If you skip gen_salt, you can just go directly to that first version where you pass in the number of rounds and skip it entirely. So that's the easier route. And I'd say that's the more secure route anyway. The third method that exists is bcrypt compare. And what that does is it compares your password, a plain text password, with a hash. And so then it's going to return a result of true or false to the callback. So if it's true, then that password has the same hash as the hash. If it gets false, then they're different. So basically, you really have only two methods to use for this library. You hash passwords and you compare them. That's it. So how do you use those hash and compare methods? So let's go over hashing first. So let's say I bring in the bcrypt library, and I can bring that in with require bcrypt. I'm going to then add 2 variables here. So I'm going to add a variable for my password. Password is password. And my rounds, I'm going to say, well, let's start it at 10. So 10 rounds of salting, and my password is password. So I can call bcrypt.hash. I'll pass in the password, the salt rounds, and here's my callback. So my callback is a function that takes 2 parameters. It takes the error and then the hash. So I have to check if there was any sort of error with doing the hash. Then I want to log it. Is one way I might kind of go about this. And then if there's not, then I'm going to say, well, let's log out the password and the hash. So I've actually got this as a code example here. Let me go back to VS Code, kill my server here. So let's go to password hashing. So this is the code example we were looking at. And I'm going to say nodemon password hashing. So I run this. So here's my password, and here's the hash it generated. Do you see that?
Yeah.
That slash stands out. Is that just a coincidence?
Huh?
The slash that's about halfway through, is that that's all part of it, or is it?
That's a good question. It's a good question. We can try to play this around with this a little bit and see if it stays there. You will notice that it starts with $2b and this $10 on a similar note. You see that?
Yeah.
But okay, so there's a few things that seem like they mean something, but in general, the first thing to realize is it looks like it's random, right? Looks like this is random. And do you have any idea how to take this back from, if I have this, can I get back to password?
No.
No. But if I say, let's run this again. Okay, I ran it again without changing the password. I would have gotten the same thing if I hadn't salted it. So let me actually mess around with the salting. Let's maybe say we say a salt of 0 rounds. Still generates something different because it's a different salt every time. Let's see if I change this to 8. Okay, so you see when I do 8, you see how this number changed? It was 10.
Yeah.
So that seems to be the number of rounds that you went through. And it needs that because when it comes back to compare it, it needs to know how many rounds of salting it went through. Does that make sense? Yep.
Yeah. Okay. One is, if in your code, you wouldn't just have a password in your code, would you? Just straight up like that?
No, that would be coming from a variable, right? That would come from the user input.
Yeah, okay. So there's that. And then the salt rounds, what's the value added each time that it's done? Like, why would you do 10 instead of just 1, for example?
10 means that it takes more work to hash it, which means it takes longer for somebody to break your database. Does that make sense?
Okay, so if you do 10, looks like you got more punctuation in there. This is
but it's just random. That's just basically coming in there random. So the slash and the dot don't really mean anything. They're just one of the characters that it uses.
So the number of rounds just changes the output that you see there.
The number of rounds changes how many rounds it does. It changes how much work that it does. So
okay, but to us it's unintelligible. It just looks like the same thing.
Yeah.
Okay.
So like if you do 1 round of hashing, it will do the hashing quicker. Versus like if I were to set this to 1,000 Let's try this just with 1,000. You notice how it kind of stalls there and sitting there?
Oh yeah, that's taking a minute.
It's taking a minute, yeah. So,
but when you go to compare, like let's say they're trying to log in, how is it going to recreate the salts to regenerate that hash?
So it turns out that the salt is part of this string, as it turns out, if I remember right.
Oh.
It's kind of embedded in there, if I remember right. So it's able to extract it. I think it ends up being it's some of the first earlier characters in there. Now this looks like it's taking forever. So 1,000's probably way too much. Let's try going back to 100. I think I'm gonna guess the 100's still gonna be a long time. And it still seems like a long time.
The 1,000 broke it.
I think 1,000 broke it. Yeah, I think you're right. Okay, so, oh, well, there it went.
Yeah, it seems to be the same number of characters long. Is that password's got 8 characters? So if it was a longer password, would there be more characters in the hash?
Nope. So the hash, as it turns out, is always the same length, regardless of how many input characters you do. So I could add a bunch of more. I'm going to go back to 10 because it seems to be not happy with these bigger numbers. But I could put in a really long password in here, and it still is going to be the same length. So the hash is always the same length. I can do the same thing with taking a really short password, and you see it's still the same length. So the hash is the same length regardless of how long your password is.
Okay. Looks like 64 characters.
Yeah. So one of the things I would say there, given that that hash is the same length, right, regardless of how many I put in, if a website tells you that you can only have 20 characters, what does that immediately tell me? It means that they're probably as soon as a website tells me like I can only have a password that's 20 characters long, it makes me wonder if they're storing it in plain text. Because if you're hashing it, it actually always goes the same length, even if you have a really long password.
What did you type in to get it to hash the password again?
Hash the password?
Yeah.
I'm just hitting save right now on this code example.
Oh, okay.
This is the code that's actually doing it. That bcrypt.hash.
Yeah, but I mean in the terminal.
Oh, yeah. Yeah, I'm just hitting Control S because I'm running it through NodeMon. So every time I save it, it reruns it. That's all. So the idea is that you can run that and it'll generate this. And then this is what you save in the database, not that. Does that follow?
Yeah.
So that you save in the database, and then later you can use compare to say, does the password they enter, does it give me the same hash? So for instance, if I'm going to check the password, let's say I pulled from the database, I have this hash, here's the password that users entered. I would then call compare. I need to kill this app and go to the other one, NodeMon password checking. So this tells me that they're true, so they're the same. So it tells me that this password is the same as that hash, basically. It gives the same hash as that, using the same salt. And if I change the password slightly, let's say I do passwords, you see it comes out false. So it runs the same algorithm on the password we give it, and if those give you the same result, then you're good. Otherwise, it comes back false. So, or I can do password with an O instead, and that doesn't match because it's not exactly the same. So, Paul, does that answer your question you had earlier of how do you check it later?
Yeah, I see that. Mm-hmm.
So you basically just take the new password that they've given you and run it through the same algorithm and see if you get the same output. So if they both come out to this, then they're the same password.
For such a complicated concept, this is surprisingly easy to integrate.
Yeah, it turns out that it really does not take much code to get it working because there's some amazing libraries out there. Like bcrypt just basically does it for you. So it turns out it's really not hard to use, but it's tremendously like a must from security standpoint. And that's a lot of times, honestly, what you find with a lot of security stuff, and especially encryption. It's like if you just use this box, your website will be so much more secure. Do you need to understand how all the inner workings work? Not really. But if you use it, it will be better. Now, if you're a hacker, if you're attacking the website, if you're some sort of security specialist, then obviously you need to know how those innards work. But for the average web developer, it's like, here it goes, just use this. And we don't usually need to know about what's going on inside. At least not very much.
So comparing this to the database stuff we've been doing for the last month or so, this is pretty easy stuff to integrate.
Yeah, it's pretty easy by comparison. You just here's a few lines of code, add it in, it works. So the actual code stuff here is pretty easy. So that's how you do the hash with callbacks. If you want to do the compare, we kind of looked at that already. Now, if you want to do the hash asynchronously, this is how you do it without callbacks. So I'm going to say await bcrypt hash. I pass in the password and the salt rounds, and it will give me back a hash. So instead of passing in a callback, I just say await.
Yeah, that's the preferred way, right?
That would be the preferred way to use this. Either way works, but I would stress using this way, the async await syntax. If you look at their NPM documentation, you'll kind of see both. You'll have to scroll down a little bit farther to see their await async version, but I want to make sure that it's here so you can kind of see how to do that. Similarly, if you're going to do a compare, there's an await async version as well. You don't pass a callback, you just set await, bcrypt and compare, and that will give you true or false. Simple as that.
I like the enthusiasm behind simple as that.
Good thing or bad thing?
This is nice.
No, I mean that's a good thing. I mean,
so that's how you use bcrypt to hash passwords and check them. Let's see where we're at for time. Yeah, so so that's kind of an intro. We've talked about encryption. We've talked about cookies. We talked about a few pieces there. I'm going to I think I'll cut it here today, and we'll finish up with the rest of this tomorrow. So tomorrow we'll talk about JSON Web Tokens, which are a way to kind of take some data and encrypt it in a way that we can use it to use it as a login token. In a way that basically because it's encrypted and because it's encrypted with private key, public key stuff, and the user doesn't have private key, basically it's a way that you can use a cookie to store their login information. Not the password, obviously. You still would be like the user ID, but in a way that you can't just edit the cookie. So We'll talk about JWT tokens tomorrow, as well as how to do implement some of this authentication stuff with middleware tomorrow. So
I had a question about the password hashing.
Yep.
So would you want to store like maybe some of your like username, user ID, and stuff that you put in the JSON web token in a hash to keep the data extra secure?
Well, remember the problem with a hash is you can't get back to the original value. The problem with a hash is you can't get back to the original value.
Well, you can always unhash it.
You can't unhash it. That's the whole point of the hash.
Yeah, that's not a thing.
Yeah, you can't unhash anything.
Well, yeah, but with bcrypt, because I've used bcrypt before, you can run their method and you can read the data inside, can't you?
But there's not an unhash method. You can hash, but you can't unhash.
Okay.
Yeah, there's no way to reverse the process. If you could reverse the process, it wouldn't be a hash. It would be an encryption. It would be a encryption algorithm. It would be symmetric or asymmetric encryption. But because it's a hash, it's not reversible. That's important. So yeah, no, generally we wouldn't hash something and then put it into the JWT token. You could, but you wouldn't really need to. So the things that we hash are going to be things like would hash the password so we can store it without storing the original thing.
All right, so we're done for today. Lecture tomorrow.
Yep. And so I don't know if I posted out the labs yet, but basically the labs for the next 2 weeks is just to take the stuff that we've learned here and apply it to your projects that you've already started. So I think most of you have a login screen already in your labs. Basically you take this and start using cookies and bcrypt and JWT, which we'll talk about tomorrow, and integrate that to your website. That's the lab.
All right, awesome.
Okay.
I'll see you all tomorrow.
Yep. Catch you tomorrow.